In this video, we're going to take up solution stoichiometry, which is really just stoichiometry problems where one of the reactants or products, or one or more of the reactants or products, is a solution instead of a pure substance. My number one goal for this video is to convince you that stoichiometry with solutions involved is not different from stoichiometry where everything is a pure substance. Okay, if you think about things in terms of the general structure we've talked about for doing the problem, then everything goes the same except for the way you turn certain things into moles. Okay. Again, it's always helpful if you can convince yourself that more problems are similar to one another instead of saying there's like 78 different kinds of problems I'm supposed to know how to do. That always feels hard if you get to where it's just seeming like there's so many different things. So why do we have a situation for solution stoichiometry? Well, the reason is because there's lots of reactions where one or more of the reactants or one or more of the products might be in solution. Okay, anytime something is dissolving in a solution, then I have something involved. I have a reactant involved that's a solution, right? There's just lots of cases where this happens. And so in environmental chemistry, in chemistry in your body, a lot of industrial processes, there's just a lot of things where this is what we have to do. If something's in solution, then you can't really do your stoichiometry calculations starting from mass because the mass of a solution is just not a handy quantity. The reason for that, of course, is that most of the solution is solvent, and the solvent is not what's actually doing the reacting in most cases, right? And so knowing the mass of solution is just not terribly useful. So what we need is a way to get to moles for solutions. And happily, we already know a way to get to moles for solutions, okay? And that pathway involves molarity. Right? Molarity is our unit of concentration. We've already learned about just how to calculate the molarity of a solution. Now we're going to start to do things with those molarities. Right? Molarity is moles of solute over liters of solution. So that says out of the three things that are in there, molarity, liters, and moles, anytime I know any two of those, I can figure out the third one. Right? Works just like if you say density is mass over volume, I'll often say, well, if you know two of those things, then you can get the third one for free, right? And so this says if I measure the volume and know the molarity, then I can get the moles. If I'm doing solution stoichiometry, again, my game plan overall works just like always. I want to do the middle of the problem, do the bulk of the calculation, the important part, where I go from amount of the thing I know about to amount of the thing I'm trying to find out about. I want to do that in moles, right? So my beginning step is always to take stuff I know and turn it into moles. If one of the things I know is the molarity and volume of a solution, then that says if I take molarity times volume, I get moles, right? So that's now my alternate pathway to moles for something that is in solution. If it's not in solution, if it's just like something we know the mass of, then we just do mass divided by molar mass and we get moles that way. Right. This is a slide or version of a slide that I just like to put up as many times as possible because it's my universal game plan for solving stoichiometry problems, right? Which says, first of all, recognize you're doing a stoichiometry problem. Realize you've got a question in front of you that asks you how much stuff is involved in a chemical reaction. Whether it's the reactant or the product, doesn't matter. It's a how much stuff kind of question. That's what stoichiometry is about. The things I need to do, I need to get a balanced equation, right? So if I don't have a balanced equation in front of me, the first thing I'm going to do is write an equation and balance it. Then I want to do moles. That says take the stuff I know and turn it into moles. When solutions are involved, the stuff I know is usually going to include molarities, concentrations, and volumes, right? If the other reactant is, say, a solid, then it's probably going to be a mass, and then I'll just do mass and molar mass to get to moles. So I have to be a little bit flexible about how to get to moles. But those are things we've already done, right? We've done calculations that say how many moles are in this much of that solution and so on. And so those are things you already know how to do. Right, mainly going to do a couple of examples in this video, right? This is a version of a problem that you might recognize. We did a version of this without involving the solution part in one of the live classes, I believe. This is a problem that was on one of my exams at some point in the past. What does it say? It says aluminum cans can dissolve in KOH. There's an equation there for it, right? And it says I want to dissolve a standard 12-ounce soft drink can, which has about 15 grams of aluminum. How many milliliters of 1.25 molar KOH do I need in order to dissolve this? Funny story, I actually remember the time this was on an exam, and I was in the classroom with people and they were taking their test, and one by one, various people would get to this problem and they would start raising their hands and saying, like, do we have to know a conversion factor for ounces or something like that? And the answer is no, because the problem would be the same if it just started with saying, like, I want 15 grams of aluminum is going to dissolve in KOH, right? The fact that it came from a 12-ounce soda can doesn't really change the problem. But having that number in there gets people sort of thrown off balance and makes you feel like you have to do something with it. That's actually an important part of problem solving, right? Is learning what information isn't important. And so just knowing that that's a thing that is, yes, it's a number, but you don't have to use it to solve the problem. All right, so here's my summary of the question. It says that the thing I know is that I want to dissolve 15 grams of aluminum. The thing I want to know is how many milliliters of this 1.25 molar KOH solution do I need? Okay, I already have a balanced equation because I was kind enough to give us one of those. And so if I look at that, I'm going to start with the thing I know. The thing I know is that I have 15 grams of aluminum. Okay, in this case, the solution is the thing I'm trying to find out about. So my molarity step is going to come at the end in this particular problem, right? Here I've got, I want to turn that into moles. So 1 mole is about 27. That many grams of aluminum, that's a mole of aluminum. I always like to put my mole to mole ratio in my equation, okay? In this case, it happens to be that it's going to work out to be 1, so if I left it out, I'd be okay, but that's a sort of bad habit to get into, and so I don't advise doing that. That needs 2 moles of KOH according to my equation. And in this case, what's going to happen is my molarity is now going to act like a conversion factor between from moles into liters, right? So this says my molarity up here says I have 1.25 moles, say, of KOH. And that would be in 1 liter. I'll put a liter up there for now. If I multiply that one out, my notes claim I get 0.445 liters. Which we can then recognize as being 445 milliliters, since my problem actually asked me for milliliters, right? So in this case, because the solution was the thing I was trying to find out about, I used this in the opposite direction, right? If I stopped here, if I stopped right there, it would say I have 0.556 moles of KOH is what I need. Right? And then if I looked at this and I said, well, I get 1.25 in a liter, so if I had to take a first guess there, I would say it's going to be a little bit less than a liter. When I actually do the math, it is in fact a bit less than a liter. So that's encouraging, right? And again, this is just a reminder, you can use the molarity here as a conversion factor, in this case, to go from moles into liters. If I had started off knowing how much solution, then I would have been using it to go from liters into moles with my molarity. That would have been the alternate approach for that. The other example I want to do is one that involves what is called titration. Titration is pretty much a chemistry-specific word. I'm not aware of it having any use in ordinary speech. And what we mean when we say something is we're going to do a titration. Generally speaking, that means we're going to find the concentration of a solution by reacting it with some carefully known amount of something else. All right. The reaction that I'm going to work with here is between sulfuric acid, H2SO4, and sodium hydroxide, NaOH, right? And I definitely picked this equation or this reaction for a reason here to make a point. That's an acid-base reaction, right? So when I do that reaction, I'm going to get water, and then I'm going to get a salt, as we saw in the last video, which says, in this case, my salt is sodium sulfate. I work out the charges to be Na2SO4 by knowing that sodium is +1. The fact that it's H2SO4 reminds me that SO4 is sulfate is 2-, so I need 2 sodiums to go with that. Obviously, I just picked some numbers here. This would be very unlikely to happen, that the numbers would all be so nice and round like that if we were really doing this, but it's an example problem, so that's okay. It says 20 milliliters of the base neutralizes 25 milliliters of 0.08 molar sulfuric acid. So this means we've already measured the concentration of the acid somehow carefully. We want to know the concentration of the base solution. The people that work in the chemistry stockroom actually do this sort of thing all the time because NaOH, you can't really make a solution of NaOH and know its concentration accurately because it starts off as a solid, but that solid just sucks up water out of the air like crazy. And so when you weigh it out, it's always got some water in it. So there's always less NaOH in your massive solid than you thought. And so we really do titrations like this to get the concentrations of the base solutions usually before they get rolled out into labs and what have you. Okay, so let's summarize what I know here. I know there's still my balanced equation up there for my reaction. I know how much acid I have. So this is the thing I know, is how much acid. This is the thing I'm trying to find out. This is also the problem that I started to warn you about when a few videos ago, I introduced you to the dilution equation, which is the somewhat notorious M1V1 equals M2V2. This is the problem that's going to tempt you to do that where you really don't want to do that. Okay, why don't you want to do that? Well, because this equation says I need 2 moles of NaOH for every 1 mole of H2SO4. So the moles do not equal the moles. That means the M times V does not equal the M times V. Better plan is just say it's a stoichiometry problem. Stuff is reacting, and it's asking me something about a how much question. In this case, the thing it's asking me is the concentration, but because I know the volume and I want to know the molarity, I could say, well, I have to know the moles, right? If I know how many moles of NaOH reacted, I can use moles and volume to get molarity, and that's what we're going to do. So I'm going to start with the thing I know, and that's this stuff. So the first thing I'm going to do is I'm going to say I have 0.025 liters, 0.025 liters times 0.080 molar. And if I multiply that out, I'll just tell you I have notes up here. It's pretty easy to do. That gives me 0.002 moles of acid, H2SO4. All right. Now what? I take my moles of acid, and I could have done this in my normal keeping going fashion. I just, for some reason, decided to break it and write again down here. There's no really good reason I had to do that. Now I go in my balanced equation, and I get my mole ratio. This is the thing that breaks the M1V1 equals M2V2 equation in this case. That says for every 1 mole of acid in this reaction, I need 2 moles of base. Right? So this is going to tell me how many moles of base I have, and it's pretty obvious that it's 0.004 moles of NaOH. I know that those moles are in this 20 milliliters, so I just take my 0.004 moles and I divide them by 0.02 liters. And when I do that, I get 0.2 molar NaOH as my concentration. Okay, you can confirm for yourself if you want, but if you do that equation with the M1V1 equals M2V2 equation, if you do that calculation with that equation, you'll end up off by a factor of 2, right? Because of the 2 moles of NaOH in there. Yes, it's possible in principle to modify that equation and stick a 2 in there, but be very careful if you do that. A lot of people trying to do that will put the 2 in the wrong place. I've seen a lot of people just do things kind of in the wrong direction by just trying to wedge a 2 into that equation. And so this is very much the situation that I was trying to allude to when I said that dilution equation is great for dilution, but it's not great for some other things. And this is one of those other things. If my reaction had been, if instead of H2SO4, if I had HCl over there, then it would have been a 1-to-1 molar ratio. And then it would have been okay, at least in the result, if I used that equation, because the moles would have equaled the moles, right? My own preference is when I'm doing a problem that just looks like, okay, that's an actual reaction going on, it's a stoichiometry problem, I like to do it like I do all the other stoichiometry problems, because I just feel really confident, yes, I can do those kinds of problems. I don't have to stop and decide, you know, is this the right time for that equation or anything like that. So I use my dilution equation for diluting, I use my stoichiometry plan for doing stoichiometry problems.